Yes, thank you very much for giving me the opportunity to give a short update on the activities of the ESM committee, which is part of the product and standard bureau led by Detlef. But I must admit that not so many things have been changed since my last report last year at IOGG, so we are still working on quite similar topics like last year. So that means the presentation is starting now. That and exactly. Thank you very much. That I have the chance and have enough time to bore you with the repetition of the general purpose, the general task of the group. And this is listed here again. I showed this first slide, many times in previous years, but please let me briefly repeat. The main intention is to advance the development of physically consistent numerical system modeling. Yes, this word, the keyword consistency, has been stressed several times, not only at this meeting, not only in the very nice previous talk by Urs, but since many years. And I will do the same. Consistency is also for this committee really the key word. Yes, and why are we working on consistency? Consistency is a precondition to promote the understanding of system processes, which are hidden in the inter-array geodetic data, which is always a sum of many simultaneously acting processes. And we have to establish links between geodetic products and process models. And links, sounds very easy, are manifold. This can be very simple. For instance, to develop tools which translate geodetic observations to model output and vice versa. But this can also be very technically, for instance, by development of sophisticated algorithms for data assimilation and all these other things. And another purpose is the preparation to geodetic products for multidisciplinary utilization. We can only contribute to that, but this is one purpose because the group is very multidisciplinary. So this is a good precondition to achieve this goal. And here are some let's say, sub-goals. To reach the general goals, it is necessary to implement relationships between various geodetic quantities like surface deformation, gravity, field variation, earth rotation, and so on. This, again, sounds very simple, but usually system models do not consider these quantities simultaneously. For instance, one of the output can be surface deformation, but surface deformation at the same time affects earth rotation and vice versa. But this is usually not implemented in numerical modeling approaches. So there's a lot of work behind this. And in addition, of course, we have to consider interactions among subsystems. Surface loading causes deformation, deformation causes gravity field effects have an effect on ocean circulation and vice versa. For this, we have to promote homogeneous processing, which finally allows effect separation of the integral data and so contributes to comprehensive interpretation of geodetic data. Yes, and last but not least, another important aspect is also a buzzword, I know, a consistent integration of various data achieved from various geodetic sensors, various observations, and so on. This one purpose is to improve the modeling approaches, but this also provides the opportunity to get an idea of the consistency of the individual observations, because they have at the same time to fulfill conservation equations. And so we can, by integration of various data into modeling, get an idea of uncertainty of geodetic observations. So what were the recent main activities the real focus was on the development and evaluation of techniques which combine data assimilation with numerical modeling approaches, as well as approaches based on artificial intelligence into model approaches, and to combine them. As another point was to evaluate the opportunities to provide realistic model error estimates. These are only two short questions, but this is effort for hundreds of people for decades. This is behind, because this is a part of the Bureau for Standards. And when you introduce standards in various modeling approaches, then you lose diversity. You introduce, for instance, certain parameters, of where these parameters are uncertain, but to define a standard. And when you then compare various models, this is not reflected in the uncertainty of models, because both use the same parameter. So you have also to find a compromise between standards and diversity of models to be able to perform intermodal comparisons, like IPCC also. Yes, and the other point there also is a contradiction of the previous slide. As I said, okay, we want to understand the processes responsible for the observed observations. But this usually cannot be done by artificial intelligence. And I will try to give an example in the next slide. What are more concrete examples? We applied several attempts, for instance, neural networks in the scale model approaches for midterm predictions of several geodetic quantities, like, for instance, rotation parameters. We performed sensitivity experiments for the importance of anelasticity and other rheological characteristics in order to improve the deformation models due to surface loading. And another point that was, yes, partly motivated by a, let's say, pioneer work on Roman Sulzbach and Hartmut there. I think it was published 2 years ago in Journal of Geodesy, where they first identified in measurements of SG these small ocean tides. And these small ocean tides become more and more important, especially due to the increased accuracy of geodetic sensors. So this is also an area of activity. And we had some discussions, of course, of the advantages, but also disadvantages of the implementation of algorithms based on artificial intelligence, and I will come to this in a minute. So, but usually this group is, of course, not, yes, the right place from which you can expect groundbreaking new scientific results. Yes, this is more a discussion club, yeah, to raise awareness. Yes, awareness of the importance of geodetic observations, for instance, for other disciplines. And this is a platform to promote development which make, for instance, sustained modeling approaches, for instance, from the climate community, applicable for geodetic questions, but also to allow to use geodetic products in these system model approaches and to improve these system modeling approaches from other communities. Here's one example, yes, which focuses in principle on the first point and the last point given here. Yes, as I mentioned, we do not usually produce new results, usually, but there, of course, there are exceptions. Sometimes there are really nice results. But I will try to illustrate the examples given here on the slide by text by means of 3 very concrete examples to give you an idea what we are doing. But these are really very, very small concrete examples. And this example first focuses on the prediction of Earth orientation parameters. And most of the results given on the left-hand side were provided by the recent, what is the second Earth orientation parameter prediction comparison campaign. Probably somebody knows better than me, but if I remember correctly, it's publicly available. You see the blue line here is the standard solution from IES Bulletin A. And you see there are several different approaches. I will not go into the details. Some include machine learning or neural networks or data assimilation and so on. But what is in common for all these solutions is that after the end of the forecast horizon of the atmospheric data is achieved, then the spread increases significantly and the error also increases significantly. Here, this is the case after 6 days, the solution becomes quite worse. But the behavior of the curves are different. For instance, very weak solution is here from data assimilation, the solid red line. One can explain this, but I do not want to go into the detail and discuss all this stuff. Instead, I would like to concentrate only on 3 curves shown on the left-hand side, which might illustrate the main point I would like to stress here. That one point, of course, is the critical horizon forecast of the forecast horizon of the atmospheric data. And the blue line represents a solution where we have a forecast horizon of 6 days, and the yellow one is of 10 days. You see, in case you increase the forecast horizon by 4 days, this is only a very, very marginal effect on the quality of the EUP prediction. Here's a forecast horizon. Again, they're similar till day 6, but then there's a spread. And what we have here on the y-axis is the mean absolute error. But what you also see, in case you introduce neural networks or machine learning approaches, you significantly can reduce for the midterm horizon of the forecast the error. 20% after 10 days, or even almost 30, and even almost 50% after 1 month. This is really a great result, but is it useful? Yes, as often, it depends on the perspective. Maybe some of you, because I'm boring you, are already looking on their smartphones, checking the newest weather prediction for the evening. What you then want to know is, to get an idea, do I need this evening an umbrella, a hat or a warm jacket, or sunscreen? Probably not in Potsdam. But you're interested in the variability of this forecast. You're interested in how much will it rain, when will it rain, where will it rain? And I guess most of you are not interested in the fact, is the model behind this forecast physically consistent? This is probably something you don't care. So you can improve this prediction by machine learning approaches. Looking for Benedict, yeah, there's the expert. He probably corrects me when I'm wrong. But these algorithms are typically so complex that you cannot reveal causative change. That means you cannot reveal the physical processes behind. You can improve the result, but this is more or less, it depends on the complexity. So they provide an improvement of the forecast, but you cannot identify the individual processes behind the observed change. This is not possible by these algorithms. So you can improve it, but this does not help to understand the processes behind. But this is the main intention of the group. I said, we need to understand the processes behind the geodetic observations in order to make them usable for other disciplines. So for our purposes, these machine learning approaches are not useful. We can improve the final product, but this does not improve our understanding of the process. So it's always a question of the perspective. And the other example here is on third-degree types. You know, when we look at the main tidal components like M2, O2, and so on, we are able with forward modeling to reproduce, let's say, 95 or even more % of the variability observed by altimetry. And we were interested, this is also possible for the very small tile effects. And this is a comparison of a forward simulation of ocean tides with terrestrial measurements of superconducting gravimetry. So this is only the comparison of the effect the ocean has on the terrestrial gravity changes. And you see here a model SG comparison. The blue line is from the model, and then the red arrow is the observation. And so the difference, or 100% minus 100, is reflecting the accuracy of the image. And you see here, even for this very small, sorry, this is what's first the main component, sorry, M2, we have as comparable agreement as we have for altimetry in the open ocean. Not 95%, but 84%. And when you look at the very small tides, the 30-degree tides shown on the right-hand side, you see even accuracy of almost 80%. And this is very, very high. Because, of course, the uncertainty of the SG observations is significantly higher in this case than in that for the main tile contributions. So this is very astonishing. And when we compare this for the open ocean, the upper line here is a result from Richard Way, who first identified the third-degree component in altimetry data in the work he published in 2020, I think. And we compared this with the forward modeling approach. Forward modeling approach means there's no data, no observation introduced. And then we calculate the difference and to see the residuals are at least one order of magnitude less than what is derived as total amplitude signal in the altimetry observation. So this is not perfect, but quite satisfying. My last example I would like to give here only implicitly touches the question related to open science and open sources and so on. Is there are many pros and cons to transfer your in-house model to a community model. But due to the fact that typically an individual institution has not the resources to regularly update and improve the model code, it makes sense to make the model approach a community model. Then a large working group is working on this code. So the question arose in the group, in the ESM group, should we completely switch to community model approaches instead of keeping all our private models? And before we can answer this question, of course, we must have a first idea on the quality of these community model approaches. And this is only one example where we compared our usually used model LSDM with the list flood approach, which is a community model. It's a much higher spatial resolution, as shown there. It's also a very good temporal resolution. And we compared this with vertical displacements derived from GNSS and with terrestrial water storage derived from race observations. And as you can see in the lower plot on the right-hand side, unfortunately, the result is more complicated than one might have expected. So there are again pros and cons. So there is no yes or no to recommend this switch. But what you should keep in mind is when you recommend a switch to a community model, then you immediately lose physical consistency. Because modelers who develop these community models do not care about mass conservation. Weather prediction models do not care about mass conservation. They want to have a good prediction of temperatures and classifications. So this would mean when we switch to community models, we do not have to regularly update our implicit code, but we are first to make it fit for geodetic applications. And this means we have to introduce algorithms which assure conservation. So it's again a trade-off how to proceed. So let me come now to an end. What are the planned actions? Yes, we will continue in our activities, as I mentioned at the very beginning, related to the coupling of approaches from artificial intelligence and data assimilation. And we will check where are the pros and cons in individual approaches. What we also should keep in mind are the developments in hardware. We cannot escape. We have to deal with these changes. And unfortunately, the developments will not at all consider the requirements from a geoscientific modeling. These changes are completely driven by economics interests. But we have to deal with that. And we should be aware this will be a significant change in model because we cannot, via the switch from supercomputing to exascale computing or quantum sense and so on, use our model codes as they are at the moment. This is not possible. So we should be aware. And of course, we have to continue about thinking about how to position to questions related to open science and open source code. So let me close my short update with one of the modeler's basic principles. A numerical model will not simulate what you want. It will simply simulate what you have coded.